All right, hello Chem 30 students. So today we're looking at balancing redox reactions using oxidation numbers. So if you remember in our last lesson, we looked at basically building up our own half reactions and then using those to balance a to create a fully balanced redox reaction. So now we're going to be looking at slightly more complex types of questions where it's more difficult to build up those half reactions. So instead we use oxidation numbers. So again, our curricular outcomes for this one are going to be pretty similar to what we saw last time. We're just adding on this last point here because this is what we looked at last time. So we're adding on assigning oxidation numbers where appropriate. I guess that's kind of not really super helpful because we already learned how to assign oxidation numbers, but you do have to be able to write and balance equations for redox reactions. Oh, right, sorry, this would be the additional part, by assigning those oxidation numbers where appropriate. Okay, so that's what we're going to look at today. So the method that we looked at so far was really good if we're working with acidic conditions or pretty simple reactions like metal-metal ion changes or non-metal and non-metal ion changes. But if we're going into something a little bit more complex or difficult to balance, then it can be helpful to use oxidation numbers to balance the reaction. Okay, so when we use this method, we're using the change in the oxidation numbers to basically understand how many electrons are being transferred per atom or molecule, and then we're kind of balancing that out through the reaction. So our basic procedure for this is to go through and assign oxidation numbers to all the entities and identify the changes, right? So you're looking for your reduction and your oxidation reaction. Then you can use the change in the oxidation numbers to determine the number of electrons that are transferred per atom. And you also need to make sure that I guess that would kind of be considered part of it. You're basically looking for, like, what would be the total within that molecule. So that's mentioned here. So looking at the number of electrons transferred per reactant. Then you're going to calculate the simplest whole number coefficients that balance the total number of electrons that are transferred. Because remember, if we have reduction and oxidation happening, of course we have to have an equal number of electrons being lost as there are being gained. So basically we want to balance that out, and we can use the balancing of the number of electrons that are transferred to represent the balancing of the reactants and products. Now, at the end of some of these reactions, if things aren't balanced, basically if your oxygen atoms aren't balanced, we're going to use the same method as we used a couple of lessons ago, where we're going to add oxygen atoms. Or was that in the last lesson? I'm losing track. Balance the oxygen atoms using water, and then we can balance the hydrogen atoms that are introduced by that water by using H+ ions. So if that seemed a little overwhelming, don't worry, because hopefully it'll make way more sense once we actually go through some examples. So in this one we have hydrogen sulfide is burned in the presence of oxygen and is converted to sulfur dioxide and water vapor. And we want to use oxidation numbers to balance the equation. So I'm just going to change things up a little bit here because I have the filled in notes, but actually when we're working on these together, it's not super helpful to have that filled in part there. It's easier if I just kind of talk you through it. So I'm just going to put some blank paper here. Of course, you can go to the filled in notes to see kind of the step-by-step description, but I'll kind of talk you through it in this video. So we have our equation here, and we want to think about what are our oxidation numbers. So for sulfur, for hydrogen, when it's combined with a non-metal, it's always +1. And then, of course, because there's two of them, we have a total of +2. And because this is a neutral molecule, we need to have -2 on the sulfur to balance that out. Oxygen is just a single element, so it has an oxidation number of 0. And then for sulfur dioxide, oxygen is going to be -2 when it's in combination with a non-metal here. And there's 2 of them, which brings the total down to -4. So for a neutral molecule like this, we need to have sulfur being +4 with its oxidation number. And then for water, hydrogen is always +1, and there's 2 of them to balance out the -2 oxidation number from the oxygen. So now we want to look at changes that happen. So hydrogen is +1 here and +1 there, so no change. Sulfur is -2 here and +4 here. So we see an increase in the oxidation number, which means that oxidation occurred. With oxygen, we have a value of, actually I might have written that in a really inconvenient place, right underneath the oxygen. So let's just do this. Oxidation. And then for the oxygen, we have an oxidation number of 0, and over here we have a value of -2. Same thing for the sulfur dioxide. So we can kind of go like this to show that both of them are reductions. Right, we have the charge is going down, or the oxidation number, sorry, is going down. That's a bad habit to call it the charge. Okay, so we have oxidation and reduction happening. Now we need to think about how many electrons are being transferred in total when we see this happening. So if we have an oxidation number of -2 here, and over here, the same element has an oxidation number of +4, that means there has to be a change in the number of electrons by 6, right? So to go from -2 to +4, we must have 6 electrons being transferred. Now there's only 1 sulfur here and 1 sulfur there, although really we only use this one as our reference. There's 1 sulfur, so in order for the oxidation value to change, there would have had to be 6 electrons transferred for just that 1 sulfur. Now with oxygen, we have the oxidation number of 0, and then on the other side it's -2. So if you have a situation like this where there's 2 possibilities and they're both the same, just use like that as your value. So in each one of these, the value changes from 0 to -2, which means that we would have had to have 2 electrons transferred. But keep in mind, because in this molecule we have 2 oxygen atoms, each one is transferring those 2 electrons. So that means we have a total of 4 electrons that are actually being transferred from that oxygen molecule. So now what we want to do is, if you think about what's happening here, we have 6 electrons being transferred and 4 electrons being transferred, which is uneven, right? Because one of these is oxidation and one is reduction. So we can't have a difference between these 2 numbers. Equal numbers of electrons need to be transferred by each reaction. And so we want these values to be the same. You just look for the lowest value that both of these numbers would go into. So that would be 12. So to make 6 into 12, we need to multiply it by 2. And to make 4 into 12, we need to multiply it by 3. So now we have equal number of electrons being transferred, which is what we want. So the value that we came up with to make those numbers equal is going to be the coefficient for the molecule that these electrons were a part of. So in this case, the 6 electron transfer was coming from H2S. So the coefficient of 2 is going to go in front of H2S. The 4 electrons that were being transferred were from the oxygen, so that needs a coefficient of 3. Okay, and so now all we have to do after that is go in and balance the rest of the components of the equation if we need to. Okay, so we have, now remember, you always want to start out with your non-hydrogen or oxygen entities. So here we have 2 sulfurs. So over here we're going to need to put a 2 in front to have 2 sulfurs. Then we can start with our hydrogen. So we have 2 times 2 is 4 hydrogens. So we're going to need a 2 out front here. And then we can look at our oxygens and see if they're balanced. So we have 2 times 2 is 4 oxygens, plus the other 2 is 6. And over here we have 3 times 2, which is 6. So there's our balanced reaction, 2, 3, 2, 2. Okay. All right, so let's try another example. I'm going to do the same thing here and grab a scrap piece of paper. So use oxidation numbers to balance the following equation. I'm actually just going to pause the video a second and write this out a little bit lower so that we can work with it more easily. Okay, so here's our reaction that we're working with, and we want to balance it out. So let's start out by assigning oxidation numbers. H is always going to be +1 with a nonmetal here, so we have +2, so this has to be -2. And then remember, in a peroxide, oxygen has a bit of a different rule. It's always -1. And then there's 2 of those, and hydrogen is still going to be +1, so they're balanced out. S8 is an element, so it's 0. And then in water, we're going to have -2 and +1. So looking at the changes that happen, hydrogen is +1, the same throughout. Sulfur is -2, changing to 0. So we see an increase in the oxidation number, which means that is an oxidation reaction. And then for the hydrogen peroxide, let's see, we have oxygen with -1, and over here it's -2. So we see the oxidation number decreasing, which means we're working with a reduction there. Okay, so once we have our changes figured out, we want to determine the number of electrons that are transferred per atom. So in this molecule, we have sulfur and there's only one atom. The change in oxidation number goes from -2 to 0, so that means we have a change of 2 electrons. And because there's only one sulfur atom in this molecule, the total change is 2 electrons. For the hydrogen peroxide, we have -1 changing to -2, so that's a change of 1 electron, but there's 2 oxygens in this molecule. So if 1 electron times by 2 molecules, so we have a total of 2 electrons transferred for the whole molecule for the reactant. So now we're in luck. This is pretty much the easiest kind of question you can get, because we're basically at a point now where let's see, we have equal values for each one of these numbers of electrons. So that means we're in a 1-to-1 ratio for these two reactants. Now, if that's all balanced out already, all we have to do is what we just did in the last one, where we balance out the other components. So remember, leaving hydrogen and oxygen for last, start with the sulfur. In this case, there's 8 sulfurs here, and there's only 1 here, so we're going to need 8 there. Now, a little bit of a hint for a question like this that can be kind of tricky is if we have 8, because we have equal values of our electrons for each reactant, if we have 8 of these molecules, in order to transfer the same number of electrons, we need the same number of molecules of the other reactant. So it's just a little bit of a trick that if you have 2 reactions that are transferring the same number of electrons, you would need the same number of each of those. And that's going to make it a lot easier instead of going back and forth this whole time trying to figure out hydrogen and oxygen, because now that we have this side balanced, we can say, we can start with hydrogen, for example. So we have 8 times 2 is 16 hydrogens, plus another 16 is 32 hydrogens. So in order to make this into 32, we need to multiply it by 16. And then we can check and see if our oxygens are good with what we've done. So we have 16 oxygens total here. We have 8 times 2 is 16 oxygens there. That's going to be your easiest way to balance this instead of trying to go back and forth between the two for a question like that. Okay, so nice to kind of keep in mind sometimes that we have these little tricks to make things easier, especially because balancing can be really labor intensive sometimes. Okay, let's try another example here. I'm just going to grab another piece of paper. Okay, so we have our reaction here. We want to assign our oxidation numbers. Now, just be aware in this one, it's saying the chloride ions and iodine react in an acidic solution to produce chloride and iodide ions, and we're balancing the equation. So just keep in mind we're working with this acidic solution. So assigning our oxidation numbers, we have -2 times by 3 is -6. We need to get to -1, so always keep in mind that charge there. So to go from -6 to -1, we need +5. We have elemental iodine, so that's going to be 0. We have an ion, so that's going to be just its charge. Again, over here, -2 times by 3 is -6. And then to get to -1, we would need to have +5 added on there. Okay, so looking at the changes that happen, we have chlorine going from +5 to -1. So that's our reduction reaction. And what else do we have? Oxygen stays the same. Iodine goes from 0 to +5. So with that increase in oxidation numbers, that means we're working with an oxidation reaction. Okay. So now we want to determine our number of electrons that are transferred in each one of these. So in order for chlorine to go from +5 to -1, that would have to be 6 electrons that were transferred. And there's only one chlorine in the molecule, so that can stay 6 electrons. Over here, to go from 0 to +5, we would need to have 5 electrons transferred. And in this molecule, we have 2 iodines. So per molecule, we have a total of 10 electrons being transferred. So now we want to balance these values. So we want to have the same number of electrons being transferred in each. So for 6 electrons and 10 electrons, the lowest number they both go into is 30. So 6 electrons times 5 will give us 30. So our coefficient for the chlorate ion is 5. And for 10 electrons, we would need to multiply by 3 to make 30 electrons. And so that's going to be our coefficient for iodine. Okay. So once we have that balanced, same steps as always, we want to balance our non-hydrogen or oxygen entities. So we have 5 chlorines here, so let's put 5 out front there. We have 6 iodines here, and here we only have 1, so let's put a 6 out front there. Then the next thing we want to look at is oxygens. So on this side we have 5 times 3 is 15 oxygens. And on this side, we have 6 times 3, which is 18 oxygens. So that means we need to add 3 oxygens to this side. And the way that we can do that is by adding 3 water molecules, right? So I'm going to go back a little bit further. 3H2O, add that in. Now I've introduced hydrogen to the equation, so I need to balance that out. So now I have 6 additional hydrogens in my reaction, so I need to balance it out on the product side by adding those hydrogen ions, 6H plus AQ. And now my whole reaction is balanced, right? So I've balanced everything in there by using water or hydrogen ions. Okay. So I think that should be everything for that one. Let's move on to our second to last example. I'm probably going to add an example here at the end that wasn't actually originally in the notes. Just because there's like one type of really complex question that's not addressed in these notes that I would like you guys to know. Hint, because it will be on the test. So yeah, we'll try and go over a question like that so that you're well prepared for kind of a more complex type of question. Okay guys, I'm just going to pause a second so I can get this written out like before. Alright, so in this one we're told that we're working with a basic solution. So just remember, just like when we were looking at balancing using half reactions, we have the option to add on at the end to balance things out, those OH ions, okay? So, assigning oxidation numbers here really quickly. Oxygen with nonmetals is going to be -2. Hydrogen is going to be +1 and +1. So that means we have a total of +4 from our hydrogens, -2 from our oxygens, leaves us at +2. So to bring us down to neutral, like the molecule is, we need -2 on that carbon. Then for our permanganate, we have -2 for our oxygen. -2 times 4 is -8. And in order to get to -1, we need to add 7 to that. On this side, we have -2 times by 3 is -6. So to get to -2, we need to add 4. So there's our carbon. -2 times by 4 is -8. So to get to -2, we need to add 6 on the manganese there. Looking at our changes that we see, it's pretty safe to say manganese will be 1. So it goes from +7 down to +6. So remember, if the oxidation number decreases, we're looking at a reduction. And what else do we have? Carbon, maybe? Carbon is -2 to +4. So that is an increase in the oxidation number, which means we're looking at the oxidation reaction there. Hydrogens and oxygens stay the same throughout. Well, there's actually no hydrogens on this side yet, so we'll have to address that later. So now we want to think about how many electrons are being transferred. So for the manganese, going from +7 to +6 means 1 electron is transferred. For the carbon, going from -2 to +4, that means we have 6 electrons being transferred. So each one of these only has one atom in their reactant molecule. So we already have the total number of electrons. Now we just need to balance. So basically we'll just have to multiply this by 6 so that we have 6 electrons from the permanganate ion. So that means we need to put in a coefficient of 6. Now we can go through and start balancing our non-hydrogen or oxygen entities. So 6 manganese means we're going to need 6 manganese over here. Let's see, what do we have here? 1 carbon seems okay. So then the next thing we want to look at is our oxygens to determine if we have to add waters. So we have 6 times 4 is 24, plus 1 is 25 oxygens. And over here we have 6 times 4 is 24, plus 3 is 27 oxygens. So we need to bring this one up by 2, which means we need to add 2 water molecules to this side of the equation. Now let's check our hydrogens. So we have 4 hydrogens in our methanol. 4 plus 4 is 8. So we have a total of 8 hydrogens on this side, none at all on this side. So that means we need to add in 8 H plus ions to the other side. Now remember that because we're in a basic solution, we need to balance out the number of hydrogen ions with the exact same number of hydroxide ions in order to maintain the fact that it's a basic solution. So just make sure you add them to both sides. So 8 OH minus. Things are getting a little tight here. Sorry, guys, that's kind of messy. Okay, so we have 8 hydroxides added to each side. Now the last step, we want to tidy this all up, which is a big chore for how I've written this out, but just make sure that you want to remember that if you have equal values of H plus and OH minus, you want to combine them. And then remember, if you have like water on both sides, you want to cancel out as many as possible. So when we combine these two, 8H plus 8OH, we're going to have 8 water molecules over here. And I'm just doing this now so we don't have to rewrite everything out later, because now I can see I'm going to have 8 water molecules on this side, and on this side I'm going to have 2. So I want to, when I write out my final version of this, I want to cancel out those 2 waters, which means I'm reducing this one to 6, right? Because I used those 2 to cancel it out. So now I can rewrite out my full equation. So starting over here, I have 8 hydroxides, and plus my CH3OH, my methanol, EQ, plus 6 permanganate ions, and we're making carbonate, plus 6 permanganate, MnO4, 2 minus, AQ, and those 6 waters, 6H2O. Okay, so there's our final balanced version of this. Okay guys, so I did just stop really quickly there and went and checked because I mentioned earlier in the video that I had recalled that there was a more complex type of a question in the exam, but I was wrong. So you guys are in luck. The types of questions that we've just completed are basically, you know, kind of the level of complexity that you would see on the test. So just make sure you've gone through lots of practice examples of these, because these questions definitely will be on the test. And a lot of times it's just being careful that you remember all of the steps, right? So the more practice questions that you've done of this, the better you will be able to do on that. So this is the end of chapter 13. You made it, kind of, because you're halfway through unit B. So there's a practice test posted for you guys. So I would definitely recommend that you go ahead and do that to make sure that you have the knowledge from this, you know, from this chapter sorted out before you move on to chapter 14. Okay, so I will see you in the next chapter.